If we're going to be able to work out things in binary system, base 2 for example, or even a base 5 question, we need to understand what happens in our own system, the decimal system that we have that's actually called base 10. If we were to look at this number, 60,237, how can we actually express this number in a different way? Well, we could say that it's the same as 6 times 10 to the power of 1, 2, 3, 4 plus 0 thousands, 10 to the power 3, plus 2 times 10 to the power 2, that's 2 hundredths, plus 3 times 10 to the power 1, that's 30, plus 7 times 10 to the power 0. Anything to the power 0 ends up being 10 to the power 0 is 1, anything to the power 0 is 1, so that ends up giving us our 7 there. So if we actually change this into some different columns, instead of calling them 10,000s, we put them in column of 10 to the power 4, 10 to the power 3, 10 to the power 2, 10 to the power 1, and 10 to the power 0. And then rewrite this number here, 60,237. Well, we have 6 numbers at 10 to the power 4, 0 numbers at 10 to the power 2, to the 10 to the power 3, 2 numbers at 10 to the power 2, that's 2 100ths, and 3 at 10 to the power 1, 3 tens are 70, and 7 multiplied by 1. So another way of expressing our number here could be expressing it in this table form. We still have the number 60,237, but we've now expressed it in terms of 10 to the power 4, 10 to the power 3, 10 to the power 2, 10 to the power 1, and 10 to the power 0. Let's say that we have now a number, instead of it being written in base 10, it's actually been written in base 5. And how would we then write a number in base 5? Well, let's take the number 1, 0, 2, 3 in base 5. And think, how would we represent that then? Well, we would do a table exactly as we did here, and we would think of 5 to the power 0, 5 to the power 1, 5 to the power 2, 5 to the power 3, 5 to the power 4. And then what do we have to think that these ones represent? Well, the 5 to the power 0 represent the number of ones that we have. The 5 to the power 1s represent the number of 5s that we have in here. The 5 to the power 2s represent the numbers that we have, that is 5 squared, which is 25. 5 to the power 3 represents 5 times 5 times 5, which is 125. Well, the way we work out what this would be in our base 5 is we just fill in the table. Starting with the units, we have 3 basic units, and then we have a 2, then we have a 0 in 5 squared, and then we have a 5 in 5 cubed. So this sort of helps us keep it nice and tidy. We actually don't need 5 to the 4 or any higher values. So our number, sorry, it should be a 1 here, of 1023 in base 5 can be written in terms of, let's see if we can create some space over here. the left-hand side here. So what do we have instead? Well, we can see that we have one lot of 5 to the power 3. Well, 5 to the power 3 is 125. So we have one lot of 125 plus 0 lots of 5 squared, which would have been 25. So 0 lots of 25, which we don't need, and 2 lots of 5 to the power 1. 2 lots of 5 to the power 1, which is just 2 times 5, plus 3 lots of 5 to the power 0, which is just 1. So we can see that we've got 125 plus 10 plus 3, giving us that 1023 in base 5 is equivalent to 138 in base 10. So just understanding the similarity between base 10 and base 5 makes these sort of calculations pretty easy to work out.